In the previous lecture, we talked about vector spaces and we set a goal for ourselves that was to get a general definition of vectors. And so now that we are equipped with that general definition of vectors, we need to figure out a way on how do we deal with these vectors or how do we handle them. So to organize our handling of the vectors, we need something that's called a basis. So let's go and define a basis, right? Okay, so a basis, I'll write it down over here. A basis in vector space V is a set of xi's, the set xi, and this set belongs to the vector space V of linearly independent vectors, right? Linearly independent vectors. And these linearly independent vectors are going to span the entire space for us. Span the space. Right? Okay. So let me just read this out again for you, even though you can see it on the screen. But a basis in a vector space V is a set of xi's that belong to the vector space itself of linearly independent vectors that spans the entire space. That is actually any element of the vector space V is a linear combination of xi's, right? Linear combination of xi, right? This set. Okay, so let's move forward, and let me just say this, that the linear independence relies only on vector addition and not on the product, right? Not on the multiplication, but only on the vector addition. So let's go ahead and check that, right? So to do that, let's say that you have a set of vectors that is xi, and they're linearly independent, is linearly independent if and only if. So this double F, this stands for if and only if the sum over I up to n, I is equal to 0 up to n, of alpha I xi is equal to 0. And this then implies that for all alpha i's are 0, right? So all of the alpha i's are 0. And so this is how we define a linearly independent set of vectors, which is according to this definition over here. Right. Now note that we have not yet required a spanning of the space, right? We have not talked about that right now. But let's, before we move further, we are going to look at some of the examples to better understand the linear dependence, right? So let's start with some examples. And we'll start with, we'll do all of these in R3, right? Okay, so in a real field of 3 dimensions. Right, now let me actually first draw some of the vectors. I'm going to draw some vectors and then I'll explain what am I doing, right? So, well, let me just do this. There is this vector and there's this vector. They're actually straight lines, right? And you have a vector that is like this, right? Now this vector is x1, and this vector over here, it is the parallel component of x1. So I'm going to write it like this: x1 parallel component, right? And then we have over here x2, right? Now if you look at this diagram that I drew with vectors, where we have two non-collinear vectors, they're always going to form a plane, as you can see from this diagram, right? And if that is the case, then they are linearly independent. So what am I saying is, now consider that you have x1 parallel component, and say that is equal to some alpha 2 times, of course, this vector, right? Because they're along that same line. So x2. Or you can also write this thing as being equal to, you can say this thing can be written as alpha 2 x2 minus x1 parallel component is equal to 0. But now see that the x1 perpendicular component, this one x1 perpendicular component, that is this one over here, that cannot be cancelled by anything that comes from this vector x2, right? And so what that means is, then we need our alpha 1 is equal to 0. That should be 0. But if alpha 1 is 0, then alpha 2 should also be equal to 0, right? And because since nothing is left to cancel out, so then if we have this thing, then if you take the sum alpha I xi, that is equal to 0. And well, that is how we define over here that a set of vectors xi is linearly independent if and only if this condition over here is satisfied. And we can clearly see in this case over here, it is indeed satisfied, right? Okay, let's consider another example where again we have in R3, right? I'm going to draw a set of vectors very quickly. So we have this vector, we have another one that is like this, and we have another one that's like this. Now this vector, let's call it x2, we're going to call this one x3, and we're going to call this one x1, right? Now here x1, x2, x3, all of these x1, x2 and x3 are coplanar. So they are coplanar, right? And if that is the case, then it is not linearly independent set. So these vectors, they do not form a linearly independent set. Okay, how? Well, consider that you have x3, right? And x3 is equal to alpha 1 x1 plus alpha 2 x2, right? And so if that's the case, then we have alpha 1 x1 plus alpha 2 x2 minus alpha 3 x3, that is equal to 0. But with alpha I is not equal to 0. And so you can see that from these two expressions over here. And so if alpha I is not equal to 0, then if we go back over here, this definition of linearly independent set of vectors is not satisfied. And so that's why we say that if x1, x2 and x3 are coplanar, then it's not a linearly independent set. Now let's go ahead and look at one last example, which is also going to be in R3, right? And let me again quickly draw a set of vectors. So we have a vector that's over here, we have a vector that's like this, we have a vector that's a bit like this, and then we have a vector that is perpendicular to this one. Let me just draw something like, yeah, so it's something like that, right? Okay, so we're going to call this one x2, we're going to call this vector x3, and if that's x3, then this is simply the parallel component of x3, and we are going to call this one as x1. Now in this diagram, or this vector diagram, of course, you can see that we have x1, x2 and x3, but they are not coplanar, right? And so if that is the case, then we say that this x1, x2, x3 indeed form a linearly independent set, right? Okay, well, again, you ask how. Let's consider that we have x3 parallel component is equal to alpha 1 x1, and by the way, whatever I'm considering, it has to satisfy what I have drew over here, so according to that diagram, right? And so it is actually indeed satisfying that. So yeah, we have a parallel component of x3 as alpha 1 x1 plus alpha 2 x2, right? And so then we have alpha 1 x1 plus alpha 2 x2 minus x3 parallel component, and this expression vanishes, so it's equal to 0. But well, what about then the perpendicular component of x3? So what about this component, this dotted line, right? Okay, so this perpendicular component, if you look at the diagram, it cannot be cancelled by a combination of vectors that are inside the plane, right? And so if that cannot happen, then that means that alpha 3 is equal to 0. And so if that's the case, then we are back at the finite case. Right. Okay, so yeah, we are done with the examples now of the linear dependence, and I hope now you understand it in a much better way, right? And now let's move on, and well, of course, then the criterion for linearly dependent vectors can be put in a more familiar fashion, right? And what am I saying is that you say that you have the set of non-zero xi's. So you have this xi and they're non-zero vectors. It is linearly dependent if and only if some xi, that is for I is greater than equal to 2 up to some n, this is a linear combination of the preceding ones, right? So the preceding vectors, right? And you look at the statement carefully again. It says that the set of non-zero xi's is linearly dependent, right, if and only if some xi, that is for I is greater than equal to 2 up to some n, is a linear combination of the preceding ones, right? And this statement, it is actually pretty clear to see this, or I mean, you don't really have to prove it, but well, we are going to prove it, right? We are going to prove this statement or this definition. It's not a definition, actually. It is just a theorem based on the definition of linear dependence and basis. Right. So we are going to prove this definition in using the if and only if statement, right? So that is that we are going to first look at the part that is for if, and then we are going to move on to the part that is for only if, right? So there will be one statement for if, and there will be another one that is for only if, right? So I hope you're getting what I'm saying. If you're not, you will eventually right now, okay? So, okay, let's go ahead and we are going to prove this statement, right? Okay, let's do that. So, say if, we're going to look at the if part, and now suppose that we start with only one of the vectors, right? So suppose we are going to start with only one of the vectors from the vector space. Now this is obviously a linearly independent set. Since why? Well, since because we have alpha 1 x1 is equal to 0, which implies that alpha 1 has to be equal to 0. Right. Now let's choose 2, right? So instead of this just 1, we can choose what is 2? N is equal to 2 for this summation, right? So I is equal to 1 to 2, right? And we have alpha I x I. Let me just yeah, exactly. Okay, so this is equal to 0 for a linearly independent, and again with this we have that alpha I is equal to 0, right? This can be true only in the case if our alpha i's are 0, right? Because xi's cannot be 0, because we said that we're dealing with a set of non-zero xi's, right? Okay, then we have that the set xi's is a linearly independent set. Otherwise, it is linearly dependent, of course. So there must be some smallest number, let's call that k. So k is some smallest number for which we can transition from a linearly independent set to a linearly dependent set. So we can make this transition, right? So let me actually write this down, that some k is a smallest number for which we can make a transition from a from a linearly independent set to a linearly dependent set. Right. That is, of course, for k minus 1. Right? I mean, not for k minus 1, of course, up to k minus 1. Right. So, well, let's write this summation down, that for summation I is equal to 1 to some k minus 1, this is k minus 1, yeah, k minus 1, alpha I xi is equal to 0, right? So again, for this linearly independence, which has to of course imply that alpha I is equal to 0, but note that for this summation, that is I is equal to 1 to some k alpha I xi, that is equal to 0. But in this case, we have alpha I is not equal to 0, right? Right? But this means that alpha k itself has to be non-zero, right? So this coefficient alpha k also have to be non-zero. Otherwise, if that was not true, then what we would have is summation I is equal to 1 up to k minus 1 of alpha I xi is equal to 0, and that would imply that alpha I is non-zero, right? So then if we say that alpha k is non-zero, right, we said that, then what we would have is x k, this vector would then be equal to minus 1 over alpha k sorry, summation I is equal to 1 to k minus 1, right, alpha I xi. Okay, so this is the if part of our proof, right, up to here. Now let's see for what? For only if, say if we start with x k is equal to this summation I is equal to 1 to k minus 1 of alpha I xi, then we just have to set alpha k as negative 1, right? And if we do that, then what we have is the summation I is equal to 1 up to k of alpha I xi, that doesn't look like x, that looks like y, yeah, so xi, that is equal to summation I is equal to 1 up to k minus 1 alpha I xi, right? So we have this k minus 1 term, and what would be the next term? That would simply be alpha k xk, and this whole thing would be then equal to we could just write it directly. Yeah, this whole thing would be equal to 0, right? Then if we go ahead and we set this thing that alpha k plus 1 is equal to alpha k plus 2 is equal to alpha k plus, well, up to so on, up to n, right? All of this is let's not just say up to n, right? Let's just say that this would be equal to alpha n. So I have dissolved k in this n, right? And so all of this is then equal to 0, because you have to keep in mind that we are talking about a linearly independent or linearly dependent sets. Right. So we have then after this that the summation I is equal to 1, I is equal to 1 to k, sorry, not to k, to n, right? Alpha I xi is simply 0, with of course some alpha I being non-zero. Now again, recall that this itself is the condition for what? Condition for linearly dependency, right? Linearly dependent. Right. Okay, now what we can do is, we are done with the proof. We should now shift our attention to the spanning of the vector space part, right? So let's go back to, or just let's go to, or let's talk about spanning, right? Okay, so a basis requires a set of linearly independent vectors which span the entire space, right? We have said this earlier. And so otherwise, for example, say you have x1 and x2, and that is in R3, would not form a basis, right? Because that's a condition, right? So if your linearly independent vectors cannot span the entire vector space, then those vectors in your vector space are not going to form a basis, right? So that means that if they form a basis, then they have to be linearly independent vectors, right? Or if they if they have to span the entire vector space, then they have to be linearly independent. We are going to look at some examples as well. Since a non-coplanar x3 wouldn't be written as a linear combination, right? So that means that if we have a set of linearly independent vectors, then they span the entire vector space. So let's just go ahead and look at an example in, of course, R3. That is, say you have a set of vectors, basis vectors, that is, say you have 1, 0, 0, and you have 0, 1, 0, and you have 0, 0, 1. Well, if you look at this set, it is a linearly independent set and it forms a basis, right? So it's going to form a basis for a vector space. But if you look at this set of vectors, that is 1, 0, 0, and 0, 1, 0, and say you have 1, 1, 1. If you look at this set also forms a basis, right? So we have this as an example, right, for linearly dependency and the spanning of a vector space. So let's go ahead and look at some more useful consequences of the basis definition now, right? So I'm going to write down a definition. That is, I'm going to write a definition as every vector has a unique representation as a linear combination of a finite basis, right? So now again, this is not a definition, it is just a theorem, right? I keep saying definition, that's my bad, but it's a theorem based on the definition of basis that we defined at the very early stage of this video. So it says every vector has a unique representation as a linear combination of a finite basis, right? So you're going to understand this much better if I prove this. So let's just not say things, but rather instead let's go ahead and prove it. So suppose there were two, that is x is equal to summation I alpha I xi, and another one that is and x is equal to summation I let's say beta I beta I and xi, right? In this case then, if we do x minus x, if we add the inverse of x to x, what we get is summation I alpha I xi minus summation I beta I xi. But then if you factor some stuff out, what you get is summation I, in brackets you have alpha I minus beta I times, of course, xi, right? And this thing is equal to 0. It has to be equal to 0, right? But recall that the only way to have this thing, that a sum is equal to 0 with a linearly independent set, is that all of the coefficients are 0. So all the alpha I, or whatever alpha I, beta I, and well up to so on, all of these are 0, right? And so hence then we cannot have a different beta I. Then this simply implies, let me write it down over here, that alpha I is equal to beta I, right? So we could have a set of alpha i's coefficients, a set of these coefficients, but we cannot have a beta I, right? So then again, this is just to say that every vector has a unique representation as a linear combination of a finite basis. So this theorem, right? And so hence here we have proved it. Okay, so let's move on and say that you have given the number of elements in any basis of a given vector space is the same, right? Then this thing is going to lead us on to a very useful definition, and this definition, let me write this down over here. It is that the dimensions of a vector space is the number of elements in any basis. Right? So let me actually, before we move on from here, give you a very quick side note that since we may always consider a vector space as a flowing of pointy objects from the origin, we may interchange the notion of vector with the location of its point in space. That is that we may interchange this thing, that the components interchanged as coordinates, right? So I might be using this word a lot instead of this one. Right, now let's finally from here move on to something that I promised you earlier in the earlier lecture or the earlier video that I made on the vector spaces. that was isomorphisms, right? So I said we are going to look at the beauty of isomorphisms. Well, first we'll have to know what are isomorphisms. So let me just actually write this down over here because I believe that it deserves it. The beauty of isomorphisms. And before I proceed any further, it has to do with the algebraic structure, right, of a group. So then we have to go back to groups for a moment, and we can have two or even more groups which are specific examples of a common underlying structure. What this means is that for each element in a group A, so you have an element G that belongs to group A, there is a corresponding element in group B. So let me just write this down over here. So this notation that I'm using is very stupid, but deal with it, right? So what I'm saying is that for each element in a group A, there is a corresponding element in group B, and of course vice versa, right? So you could go back to say you have an element in group B, and then there is a corresponding element to that in group A, right? And moreover, both of these sets satisfy the same algebraic structure, right? And if this is the case, then we say that the group are isomorphic. The groups are called isomorphic groups. Now, recall from group theory that to see the algebraic structure of a finite group, we only need its multiplication table, right? So if you have any idea, which I think you do, about group theory, at the very basic beginning of group theory, we see that to understand or just to see the algebraic structure of a finite group, we only need to look at its multiplication table. And let me actually go ahead and give you some examples. So say you have this set that is of 1 minus 1, right? And with the operation multiplication, you can draw the multiplication table as 1 minus 1, 1 minus 1. Now just perform this operation, that is 1 times 1 is 1, minus 1 times 1 is minus 1, 1 times minus 1 is minus 1, and minus 1 times minus 1 is 1, right? And let's do another one, that is the set of E and 0, and this one the so we have E0, E0, and we would have inside E0, 0, E. For just yeah, now let's just do another one, that is identity and some rotation by pi. Yeah, so this set, the multiplication table for this set would be yeah, so we have identity over here, we have r rotation with pi over here, we have identity over here, r sorry, not 2 pi, just pi, right? Now you have this identity times identity is identity. Over here we would have r pi, here we would have r pi, over here we would have r pi and again r pi, which is the same as r 2 pi, and if you do a rotation of 2 pi, you go back to the original structure, then so that means that we would have identity over here. Now note that all of these multiplication tables that I have written over here, they have a same algebraic structure, right? And so, well, in fact, any of the two element groups have a same algebraic structure, right? But it has to go in both ways. So even though we have, or we can map the rotations in 2 dimensions to a subset of rotations in 3 dimensions, we cannot map all of the 3 dimensions rotations in 2 dimensions. So what that simply means or implies is that rotations in 2 dimensions and 3 dimensions are not isomorphic, right? Okay, so let's just get back to vectors now, right? So back to vectors, I mean, because that's what the video is about, right? A very interesting feature about vectors is that they have a very well-defined algebraic structure. So vectors have a well-defined algebraic structure. And so that is why we had to discuss isomorphisms in the first place. But this will have a very important, or a consequence, you can just say, a consequence that we shall visit, right? Okay, so let's now actually go ahead and write down a definition, and that is two vector spaces U and V, right? But they have to be over same field, right? So over same field, they are isomorphic to each other, are isomorphic if there exists a one-to-one correspondence. Right? But a one-to-one correspondence between what? Right? Between xi that belongs to U, right? So xi belongs to vector space U, and some yi's, right? These vectors, this set of vectors that belongs to some vector space, or not some vector space, but the vector space V, right? And of course vice versa. Again, let me go ahead and repeat what I just said, that two vector spaces U and V that are over a same field, these two are isomorphic if there exists a one-to-one correspondence between the vectors that belong to the vector space U, which I said are xi, and the vectors that belong to V, which I said are some yi, right? And so that we can say that yi is equal to some function of xi, right, such that the function of alpha 1 x1 plus alpha 2 x2 is equal to alpha 1 times the function of x1 plus alpha 2 times the function of x2, right? So if you can you write this thing, right? But this also implies something that is actually very powerful due to the common algebraic structure. That is that every n dimension vector, let me just write it down properly. Yeah, so every n dimension vector space, that is Vn over some field that is F over a field F, is isomorphic to the field Fn, right? And then the immediate consequence of this is that any two vector spaces with the same dimensions and over the same field are isomorphic to Fn, and then of course therefore isomorphic to each other. Right, at last we have fully equipped ourselves with at least the finite vector spaces. So we are done with understanding the finite vector spaces, as I in the first video also mentioned that we have we don't only have finite vector spaces, but we also have infinite vector spaces, which are known as the Hilbert spaces and are used in quantum mechanics. But so far we have equipped ourselves with finite vector spaces, and so whenever you get something that you want so badly, the question arises, well, what do I do with this damn thing, right? And this is the question that I will try to answer in the next lecture.